So I'm Punya, I'm your TA, and I'm going to talk today about the project, what you have to do, the details of, where you put stuff, etc., submissions, and about the first part of your project, which is the scanner and the parser. So here's sort of general information about the, just working with 6035. We're going to give each group a piece of the 6035 locker. You're going to keep all your files in 6035 groups, LE something, LE01, LE02. And note that we currently don't have any controls on how much stuff you put there, so please be considerate. If you put loads of files there, you will be killing space that is for others. So take care. I have your sign-up sheets here. I will be allocating groups for those people who haven't already got groups at the end of this class, and I'll send out mail and permissions and so on by the end of the day. The way these group lockers work is you have access to them, we have access to them, no one else. So for example, other groups can't read or write to them, which is a good thing. I think one of you wrote to me about issues running Java 1.5 on Athena. So did that fix work? Okay, well. And I like the version of Ant that comes with 170. It's recent. It has a bunch of nice features. Use it if you can. And code samples are going to be at this location. You don't need to take this down. I'll put a link to this website to this presentation on the website. So, part one, the scanner. Does someone want to tell me what a scanner does, even though it's on the screen there? No. So you have a big program. It's a bunch of bytes, and you want some of it to make you want the compiler to care about some parts of it and not to care about some parts. For example, if you have a string and there's stuff inside the string, the compiler doesn't really care what's in the string. It does want to know where the string begins and where it ends. So it can take that entire block, make it into one token, and then store it as such. So comments, white space, all get thrown away at this stage. This place is also where you make the distinction between keywords and identifiers. So in decaf, for example, the word class is a keyword. You cannot use class as the name of a variable because the scanner recognizes it as something special to the compiler. Anything that, excuse me? Is there a question? Sorry. Anything that is not a keyword but isn't funny, as in it doesn't have dollar signs and dots in the middle of it, is waiting to become an identifier, which you can use as a variable, a function name, or something similar. So here's our first example of a scanner, or what a scanner does. It should be fairly self-explanatory. Anything? Awesome. So you will note that idents and strings are annotated tokens. So you have a token with some extra information alongside. Similarly for nums. When you design your data structures for these tokens, and typically you'll have cup do that for you, it'll make all these various kinds of tokens, and you can access the contents of the token. So you have keywords, which are just freestanding, and you have things like strings, numbers, which have a value. I'll talk about how you would access those values a little later. So how do we write scanners? Writing scanners by hand is not fun. Has anyone here tried writing one of these by hand, maybe in high school or something? Like tried to parse a text file? Yeah, so how did you have fun? No? No? Yeah, it's I remember writing one of these for a basic interpreter in 12th grade, and it was not fun. It was, I mean, I did a lot of bad things. I sort of wrote the scanner, the parser, and the interpreter, the actual running of the code, all together in one function. I don't ever want to see that code again in my life. Excuse me. So what we're going to do in this course is to use a tool called JLex, which is the Java version of a popular C tool called Lex. The way this works is you write a .lex file, which has rules. The rules look kind of like the rules I have here. And JLex takes the rules and converts them into a series of functions which generate tokens. So in this case, for example, the rules say, if you see the sequence of characters if, then return the if token. There's some boilerplate code here, the talk function, that I haven't shown you. It's there in the sample code. You can read it. The next line is more interesting. So what's going on here? Anyone care to explain? Someone else? Okay.
So a regular expression that matches like a sequence of letters and numbers, starts with a letter, and goes any amount of letters and numbers.
Thank you. So that's exactly right. And as you can see, this is an identifier. So these are not the rules we're going to use in decaf. Decaf identifiers are different because, has anyone read the grammar yet? Well, decaf identifiers, I think, are allowed to have lowercase and uppercase letters and underscores and stuff. So you can see. But this is the basic idea. Now, JLex has this cool feature where you can say, let me define, and you can do something like alpha plus to mean A to Z plus. This looks like a useful feature, but it's not as useful as you might think. You can never make two macros of this sort that recurse on each other, or one macro that recurses on itself. So one thing you can never ever do with JLex is balance parentheses. Has anyone here taken 6045, 6840, one of those classes? So there are theorems that state why it's impossible to use regular expressions to do things like this. Regular expressions always work with finite memory. We're going to talk about finite automata and non-deterministic finite automata later in class, and you'll see exactly why. So any questions about scanners? Please.
I've heard the term Parser used. Is that the same thing as a scanner?
Yeah. Anything else? So the next phase, once we have our stream of tokens coming out of the scanner, is to parse it. Now, what does it mean to parse a program? Well, parsing is a term taken from linguistics. When you have a sentence, you want to break it up into noun phrases, verb phrases, and so on. So if I say, the cat that ate the rat died, then the subject is the cat that ate the rat. Now the subject has other parts inside of it, which could themselves be subjects of other sentences, or verbs, or adjectives. So in the end, you take this string and you break it up into a tree of meaningful parts, like so. Now, parsing is interesting because you can't just take a random substring of this and assume that it makes sense. For example, the rat died is not part of the semantic content of this sentence, right? When I say the cat that ate the rat died, that doesn't. So what's really going on here is the cat that ate the rat died. So this is subject, object, verb, and the subject itself consists of the cat that ate. So there's within the subject there's a noun phrase and there's a predicate. Anyway, so that's a parse tree for English. So Saman yesterday talked about why English is a bad idea for compilers. It's because parse trees for English can be enormously complicated and ambiguous and hard to figure out with just 3 months of code. So we're going to have parse trees for compiler languages. This is easy enough. If I write a assign a plus 1 or a equals a plus 1, then that parses to an assignment. You're assigning the identifier a to the expression something plus something, where the first something is a and the second something is the number 1. Easy enough? When you write decaf parsers, you're going to have parse trees for much bigger syntactic structures. You're going to have a parse tree for a parse tree for a program, for blocks, for if statements, all the way down to expressions and terms and so on. So this is maybe what your parse trees will look like at the lowest level of granularity. I have a friend who took this class 2 years back, and he decided that he'd print out a parse tree of like an entire big program. I think it took up the entire wall. So if any one of you is looking for wallpaper ideas for their room, then this is great. So just like we have, just like we use JLEX to generate scanners, we're going to use COP to generate parsers. COP takes a parser specification as input and gives you 2 files, parser.java and sim.java. These perform distinct functions. Do you remember we used sim.if and sim.id in the Lexer example? Those symbols, those static definitions of variables were made by COP. So sim.java will contain all the tokens for your language. Now, from COP's point of view, your tokens are terminals. What a terminal means is a chunk of syntax that you can't decompose any further. As far as COP is concerned, that's one block or one token. So tokens become terminals, and more complex structures that you make out of tokens are non-terminals. So, for example, this noun phrase consists of an article and a noun, and in this case, the and cat would be tokens or terminals, while in everything else above that, the articles, noun phrases, subjects, etc., would be non-terminals. They're not. So, if you're wondering why we call them terminals or non-terminals, it's because once you've parsed a terminal, you can stop parsing at that point. You don't have to think any further. But if you decide at some point that, oh look, I have a subject to parse, then you have a lot more work to do at that. You have to decide what's sitting inside the subject. Is there an NP in the beginning? Is there something else? What's going on? So terminal versus non-terminal. The COP syntax shouldn't be very hard to understand. We're saying that we declare our terminals and non-terminals. By convention, terminals are capitalized, non-terminals aren't. And when I say start with, what I mean is you can parse the entire chunk of text that I'm going to give you into a non-terminal with name assign. The reason that's important is that a parser has state that tells it what to try to parse. And this is what gives it that state in the beginning. There have got to be questions at this point. I'm not that good. Anyone? Okay, so I am that good. Awesome. Can someone tell me what's wrong with this? I've made a mistake. No, that's right. Go on.
Oh, you did that or so I think the one the right. Well, no, you.
I made a mistake on the slide. The slide is
The one should be on the left.
yeah. You know, this slide kind of implicitly assumes that plus is commutative, and we're just parsing. We don't know anything about what plus means. So you're right. I shouldn't have the one on the right side. I should have the one on the left side. Okay, so if you can fix that in your minds, then the question still remains: should I parse this as, you know, plus of or the sum of 2 and 3 and 1, or the sum of 1 and 2 and 3? Now, we know from math that it doesn't matter for plus, but if I had times in one of those places, then it would matter, right? No? Right. So if I had times, it would matter. If I had a minus sign, it would matter. I mean, if I have 3 minus 2 minus 1, then it's conventional to treat this as 3 minus 2 minus 1. Right? So we say that minus associates in a certain way. So the way we resolve these problems, or one way to resolve these problems, is to sit down and make separate productions, to say, well, we're going to have one level of grammar for plus and another level for times, so on down to the bottom. I could say that a minus expression consists of a number followed by a minus. You know, I could really drill very deep down into the grammar and try to fix it, little bit by little bit. Another way you can do it that cup lets you get away with is to say, you know, it associates, minus associates to the left, or times binds tighter than plus. You can use these things to get around having to write very complicated grammars. The flip side is, when things go wrong, you'll get very puzzling error messages. You know, you'll have conflicts between things that you didn't write, because it's making up grammar rules to make up for your ambiguous grammar. Did I make it clear what an ambiguous grammar is? I haven't used the word before, but does it make sense why I'm calling this grammar ambiguous? Were you saying something?
Throw out the grammar rule for plus. That would produce both that expression. You write out the rule for plus, that would produce either one or the other trees.
Well, my point was that if we just have this rule, it could be one or the other. I mean, we haven't told the compiler which one to use. We haven't told cup which one to use, and in fact, it's going to complain and say, "I don't know which one to use. There's a conflict." Did that answer your question? I could. Sorry.
Oh, you want to keep going? Some people have those big. You see those big things of what operators take precedence. Each one is a different level of grammar.
Right. So you can do that. Or what you can also do is you can write it pretending that it will take care of itself, and then in the end say in the end say that this has greater precedence. So I can work through an example for the plus and times case to see how we can resolve this. Suppose I want to I want to parse expressions of the form right? So we have plus, times, and parentheses. How many people have seen this before? Like how to parse these? Anyone? So okay. So you've seen them before. Good. So this is actually going to be useful to people. Excellent. The idea behind parsing this is you want paren to bind very tightly. You want star to bind less tightly than paren, and plus to bind least tightly. So what we're going to do is we're going to have three non-terminals: expression, term, and factor. An expression is just the whole thing. A term is something that you can add. So 1 is a term, 2 times 3 plus 4 is a term, 3 is a term. That makes sense? And a factor is something that you multiply. So 2 is also a factor. This parenthesized expression is a factor. So I'd like people to suggest productions. What rules should I have here? I'll start you off. Just a number, If you aren't sure what syntax to use, just say something and I'll try to write it the correct way. So don't worry about that.
Terms are numbers too.
So the way I was hoping to take that into account was to say that factors are terms too. Should I write that down?
Yeah.
And in a similar vein, expressions are terms too, right? You could have just a term by itself. That would be an expression. More ideas? So how would you like to take care of things like one term followed by a plus followed by other stuff? How should we represent that? Someone else? I'd like people to answer. Let's glance back at what was happening here. What we said here was really simple. We said an expression can be an expression followed by a plus followed by another expression. And the reason there was ambiguity there was that the expression on the left, the plus here could have bound to the question was, is it this plus we're talking about or is it this one? Right? It could have been either, and we didn't say which. I'd like someone to propose a fix that doesn't have this problem here.
Expression is a factor plus factor.
So that's a good idea. Let's see what happens then. The way I intended it was for expression to be term. Factors are things you multiply, terms are things you add. So I think maybe you meant expression is term plus term.
Oh, yeah, term. Yeah.
It's all good. that's a good start, but there's something wrong with it. Someone want to tell me what went wrong here? I mean, how do I parse something like 1 plus 2 plus 3? So it's going to start off, say, 1 is a term. There's a plus.
Expression.
Excellent. Thank you. So now you've seen the expression version. What's the factor version? Or you know, what should I write down for term? It's just like this. Someone?
Term equals factor times expression.
Factor times. So if it were factor times expression, then think about what happens here.
Factor times term.
Does everyone see what's going on here? Raise your hand if you don't.
I think I get mixed up with what you were saying. Term is something that is multiplied.
That is added.
Oh, term is added.
I'm sorry. Factor, you know,
Oh, okay. Factor is the
factor is what you multiply, term is what you add. This might not be readable anymore. Anyway. So that's expression and that's term. How are we dealing with parentheses? Someone else? Come on. So here's a hint, it's a factor production. We already know that numbers by themselves are factors. What other kind of factor can you imagine? So let me ask you another question then. What sort of thing do you expect to find inside the parentheses? Can you give me a non-terminal that captures what's going to be inside the parentheses?
Expression.
It's an expression. Perfect. So it's L per n expression Raise your hand if you don't know what's going on, and I'm not making any sense at all.
That's what a factor can be.
Yeah.
Not necessarily.
So these are all the things that this is an exhaustive list of what factors can be.
It's not like the right-hand side replaces the left.
Excuse me?
They go in order?
There's no, well, the way I've presented it so far, there's no order. But you can tell COP that things that appear higher or lower have higher precedence. This grammar is unambiguous. I mean, if I give you any expression of this form, then there's always exactly one choice to take. I haven't proven this. I'm not going to prove this, but do people see intuitively why this should be the case? Let's try parsing this, right? So I start off here, and I see a 1. I want to parse an expression. So that's what I meant by the start with non-terminal. I'm starting with the intention of parsing an expression. Now, if I want to parse an expression, and I see a 1, then an expression could be a term by itself or a term plus expression. This tells me that in either case, I want to start parsing a term, right? I mean, if I have any hope, if I want to have any hope of finishing by parsing an expression, I'd better parse a term now. Okay, so now I want to parse a term. I see a 1. I look at the rules. I could parse a factor, or I could parse a factor. Okay, parse a factor. And the factor rules say you either want a number or you want something that starts with an L per n. Do we see an L per n here? No. So there's a number, and we can parse this out to be a factor, which is then a term, and we are back at the expression rule. And now we see a plus sign, so we use this rule instead of the other possibility, and so on. Make sense? Now, the important thing to realize is, just because of the precedence levels of plus, times, and paren, we had to write 6 rules. It would be nice if we could just say expressions are expressions plus expressions, or expressions times expressions, or parenthesized expressions. Everyone here has used scheme, right? There's no precedence. Life is easy. You can say plus times grouping, and you're done. Nothing further to think about. You can in fact get away with doing that, with just saying that much, if you're willing to use precedence directives that tell cup that things bind to the right, or that things bind more tightly than other things. So that's all for parser generation and ambiguity.
I'm still kind of confused on your example. Would I do the addition first then? I'm not sure how the multiplication would get.
Okay, so let's. Are we talking about this example or this one?
That one.
This one?
No, the one on the right.
This one.
I think that you just went over, right?
Okay. So, all right. What do you think is going to go wrong, or is it just not clear what's going to happen?
I guess it's looking for an expression.
Right. So it starts out looking for an expression.
So it needs to either get a term or a term plus expression.
Right. So it needs to start by getting a term, and then once it's finished the term, it can look for what to do next. Right. I mean, there are 2 rules for expression, either this one or this one. Both of them have this common prefix, and then at the end of it, you can either decide, oh, this is the end, or you can decide there's a plus trailing, I can go with this. That makes sense? So in this case, you parse 1 out as a term, you see the plus, and so because you want to be as greedy as possible, I haven't mentioned this. This has been kind of implicit in what I've been saying. The parser tries to be greedy. If it sees a plus, it tries to match the plus. It doesn't say, oh, you know what, I've seen the 1, I have an expression, I'm done. There's a plus left, so it grabs that. Yeah. So it grabs the plus and then says, oh, now I want to parse another expression.
Oh, okay. So it parses recursively, so it does that first.
Right. So 1 plus expression, which is term, which starts with factor. There's a times, so let's parse another factor, which is L per n, so parse expression, and so on. Am I making sense? Have I lost 50% yet? Okay. There's this measure with drugs. My friends at companies like DuPont tell me that you give them to rats, and then once 50% die, like that's a measure of how lethal the drug is, and then you make cosmetics out of it and give them to people. It's pretty fun, I'm told. All right, so errors. We all love errors, right? You will learn to love errors because when I wrote my first compiler, the error message, there was one error message, and it said error. this is really nice. You know that there's an error. It's good. But if you have a 500-line program and no clue what exactly went wrong or in what phase, it's not helpful. So we have several goals with errors. We want to report lots of errors. When you run Java, typically it reports 100 errors and then stops. Have people seen this? You write a huge program for 170, you're confident it works, you missed out one semicolon, and then it gets confused and gives you 100 errors. It's a lot of fun. The other thing is you want to be accurate. A lot of old C compilers report a missing semicolon on the next line. Have people seen this? Because it doesn't really care about white space, and the point at which the compiler gets confused is when it sees the next token without a semicolon, which is at the next line. So it reports the error. And you want to have a specific message. If there's a problem with a variable type, you don't want to say syntax error. I think QBasic used to do this, syntax error for everything. Then again, this is just a class. You're not making an industrial strength compiler. We don't really care what your errors look like, but you will. When you're spending late nights in November, not that you will, I'm sure everyone will finish this by 7:30 in the evening. But if you're spending late nights, then it's nice to have good errors. So the way to do this is, I was showing you some some Lexer rules here. The Lexer rules in this case just said, there's a symbol if, and there's an ID symbol, here's the contents, and that's it. You also want to remember where you saw it. So which line, which column. It's going to be useful later. When you find an error, maybe way down later when you're checking types, and you find someone's doing string plus, integer plus Boolean, and you don't know what to do with that. At that point, you want to know where in the code that happened. You don't want to say, oh, well, it was somewhere in the syntax tree. That's not useful to whoever's debugging the code. So remember to save line number information. And in the parser, I think we'll have more to say about this as we get to the parser sort of in detail. But if you can't parse something, imagine for a moment that this was imagine that you were trying to parse this. So you would start out wanting to parse an expression, 1 plus, things are going well so far. You want to parse an expression. Now, deep inside the recursion, you discover, oh wait, it's not an expression, right? You see this str thing, which doesn't match any of your rules. Now, one thing you could do is you could bail out. You could just say, well, I'm confused now. I don't know what to do. There's a thing I don't know how to deal with, so I'll just exit and report one error very precisely and leave. This has been done, and it's sometimes useful. Like if it makes your compiler a lot less complex, and it gives you quick turnaround times because you have less. If you just say, I will not get confused, I will just stop whenever I see my first error, you can get quick turnaround time. Another approach might be to say, well, now I'm seeing something that I don't know how to deal with. That's fine. I'll take it in my stride. I'll make this into an error token and keep parsing till I can find something that I can deal with. So maybe there's a semicolon at the end of this, and then there's more stuff that you could make sense of. Report an error for the str, and then keep going. We'll talk about how you can do this. Now, for the actual, what you have to type in, I highly recommend that you use ant or make or something like that. Has everyone taken 170 here? 170 or like a software engineering class? Good. Really, please. You're going to be generating files in multiple, you're going to be compiling in multiple levels because you have to have one phase where you update the Lexer, and then you make something out of it, and then that goes into your classes. If you do this by hand, you will be in a world of pain. Please don't do it. Here's a sample ant target to do what you want to do. Again, this is there. This is included in the sample code that I was talking about earlier. Here's the parser. A little bit got cut off. Same idea. And that's my final message. Questions?
Is this available online?
Yes, it will be soon. There's a slightly older version, like 2 hours older, that is up on the site, but I made some changes since then. Do you have a question? So I'm going to go to a terminal window and show you how I did this, or show you actually running this minimal lecture and parser. Can everyone read the text in the terminal windows? In back? Okay, good. So here we are. I have a copy of this in my own directory. I don't want to edit stuff here. So here we are. It's probably a little hard to read because, okay.
Sorry, can you turn on all
Yeah. I just realized. Thank you. So I've put all the targets into one ant build file, a bunch of properties set up here that maybe you can reuse to keep your directory straight. So here's what we were using for cup. This is the grammar I just showed you. Can people see that? It's the same grammar? Okay, good. So they decided to call, yeah, so they want to start with X per list. Notice that what's going on here is they're associating the other way, where I had left associative expressions. So parse, parse a factor or parse a term, parse a plus, and then another expression. What they have is parse an expression, a plus, and another term. It's recursing on the right side, which is practically the same thing for plus, not for minus. For minus, they're right, I'm wrong. Do people see why? So imagine doing the same thing for minus. What goes wrong? Here's one parse tree for minus. Which of those trees are we going to get if we use a grammar similar to that one? How many people think that we're going to get one? We're going to get one. And, okay, so everyone else has no opinion or thinks it's two. Safe? Okay. So the reason we're going to get one is that we start off by trying to parse an expression, parse the three out, see a minus, and want to parse the rest. So you get this, but this is wrong. You want the answer of this thing, you want this to evaluate to 0 and not to 2, right? Which is why they have right recursive rules. So that's their do people see what's going on here? You know, really simple tokens. If you see a semicolon, return the symbol semi. We defined sim.semi, sim.plus, and so on in the .cup file. So a warning here, the ant that's pre-installed with Athena does not support some of the attributes I used here, which is why I recommend the newer version in the 6170 locker.
Is that like a program?
Uh-huh. Did you take 170? Or?
Yeah.
Did they use ant in that, or maybe they used Eclipse?
Yeah, they just switched over.
I'm sorry. So for people who haven't used ant and want to learn how to use ant, you can send me a mail and I'll maybe set up an office hour session or something. You could use Eclipse to do this. I haven't explicitly tried to get it working, but if enough people are interested, I could do that too.
Isn't ant pretty much the same as make?
It is, except I find it easier to use. If you prefer make, go for it. It works. Does everyone see the bottom, the actual running program? So if I type in expression semicolon, I get the value out. Excellent. So we're done for today. So that's what happens if you give it an error.